Okay, now today we're going to start with astrophysics. So I'm going to continue to the next module. The last module was 1A, now it's 1B. And this module is called Celestial Mechanics. We're going to focus on calculating the orbits now. Okay, so let's start. I actually done this in our last course. But I think we only used Lagrangian. Yeah, we used only Lagrangian, and then this time I don't think we're going to use Lagrangian, but we'll see where we go. I'm not close to finished on this guy, but it's all right. Okay, so celestial mechanics, calculating the orbits. Okay, so we are starting with the first thing we are going to start with is, and we need some math, and we're starting with a differential equation. That's very, I'm so used to partial. Do the derivative twice of some function. We do that, of course, on the basis on x squared. That's equal to some function s of x, right? This is, we have done this multiple times before. It's like Newton's second law, some force, pretty simple. Okay. So, but we are going to tackle this from scratch again, even though, yeah, I've seen that before. But yeah, I actually don't know why we're doing this again. Maybe just for repetition. It's all right. Okay. Yeah. So this guy can be solved analytically or numerically, of course, depending on this guy right here. Because f, I forgot to say, f is the unknown. And s of x is, of course, known. This is a differential equation. So we're going to start numerically. That's pretty easy. Okay, then we can solve it anyhow. So this differential equation right here, how would we solve it numerically? We would start with the simpler case. Of course, there's a single derivative. df of x divided by dx is gx. Now we can do this as proper physicists and just do algebra on the dx. That's what we always do. Then we get dx on this side. And that's pretty neat. That states that if I, in order to move the function, which I don't know, in order to create some distance on it, all I need to do is move a distance with the dx, right? In terms of gx, right? It's very much like if I know the velocity, but I don't know the distance, I just, for a small step size, I moved one step forward, I can see the distance I covered behind me. That's the whole idea here. Okay. Then we have that. Pretty neat. Then we can start modeling, because now what I can say is that, because this will be, of course, the next value. And of course, like with the example I just said, we need to know, of course, the starting. So we need to know the initial condition. So I need to know x0, because then I, of course, can know f of x0, right? Because from x0, all I need to do is just go a little step, etc., right? This means that we can write that f of n plus 1, the next value, is actually just the value we are at now, plus g of x, and of course some small delta x like that. So that's a nice modeling of that, right? Okay. We can, of course, apply that to the top equation. That works as well. So now I could state, instead of that, I could state that the derivative of n plus 1 is, of course, equal to f of the derivative and 1, and then plus s of x and, of course, delta x, right? That's just if we did I'm not going to, yeah, I can explain. That's just d of dx and around. Now we have all of this in there. That's why. Okay, this is all right. But we can go one step further now, because I can apply the same idea to this guy. So just do it again. It's like going from acceleration, velocity, and then distance. That's also a typical thing you would do with the Euler method. So which is what this is. Okay. Now let's model this guy. So I wrote f derivative, didn't I? And now I want f1, and f1 is, of course, just equal to, f of n plus 1, if we do it again, is, of course, just equal to f1 plus And this is the Euler-Krömer method. So what you do, instead of using f derivative of 1, you actually use the value we got here. So f derivative of n plus 1, like that, and you multiply that by a small step size. And that's it. That's the Euler-Krömer method. And if you do this, you of course solve that differential equation. That's it. Okay, pretty simple. We've done this a lot of times in programming, actually. Okay, perfect. So now we have the math. Now we can move on to more physics. But before we do that, also we can solve this analytically. Is s x, if it's equal to minus fx plus c. And we know this equation, it's the harmonic oscillator. This one is pretty, you've seen this so many times. You know, v squared is minus v0, for example, right? Yeah, so that's also works. But of course, the harmonic oscillator, was that correct? I think so. I've written this equation, that equation there, I've written that numerous times, but I don't remember if that's correct for some reason. Wasn't it? Yeah, it's not that important, but that's a bit fun. But of course, with this function, why this is the harmonic oscillator, because we know for the harmonic oscillator it should be, there's some what you say, repeating motion, right? That should be cosine and sine. And of course, if I do the derivative twice, I of course get back what I already have, which is what happens here, right? So of course, for example, this could be a cosine of x minus omega, where a is a constant omega depending on the initial condition. So that's a way of solving this analytically. I've done that numerous times, so we're just going to keep going on. And finally, we can do some physics. So, of course, with orbits, it's Kepler's laws. Okay, so he deduced 3 laws. The third one I haven't actually done a lot, so I don't completely know the physical interpretation, but the 2 others are pretty simple. So we deduced 3 laws. The first is very obvious. I've done that in math and in physics. And of course, when you have an ellipse, it also have 2 foci. But in our case, with a planet, one of those foci, the first law is that a planet will move in an ellipse, of course, because it's very unlikely to move in just a perfect circle. Then the energy level has to be just 0. That doesn't make any sense. And then it moves in an ellipse, and it has the sun at one of those 2 foci, right? Because it has 2 foci, as you can see. And of course, sun is going to be one of them, right? And then the second one is also pretty easy. If I drew a little bit a better ellipse, let's see the second one. Maybe, no, that's not good. Maybe I can draw a big one. Oh, that was also crazy. If I move this guy, it makes, there you go. Okay. The third one is that the total area swept in time is of course equal. So if I moved from here to here, right? I will move this distance here, right? Pretty fast because I'm close to the sun. When I'm close to the sun, my acceleration is big, right? So of course I get more and more force of gravity here, and of course I'll move fast. But when I'm further out here, right? If I'm out here, I will not have the same, I will not have that big angle. I will have a very small angle because I'm very much away from the sun. And my speed is pretty slow, right? Or my velocity, of course, is pretty slow. So when I'm going around here, I'm pretty slow. But since I'm so long from the sun, I will cover a lot of area. Now the time it takes from here to here, if they are equal, the area here and the area here is the same. And you can see that's pretty clear, right? I'm fast here, but I'm close to the sun. So this area, but here, I'm further from the sun. But there's a lot of area here, right? So these 2 areas are going to be equal. So area swept in time are going to be equal. That is what it is. So yeah. Equal areas in equal times, right? So the last one makes sense. I just haven't done the calculations on it. And the last one is that if you have an orbital period around the Sun, the orbital period around the Sun and the semi-major axis, you have two axes, right? As you can see here, we have the axis in terms of the height here and in terms of this guy here, right? So there will be two. We have the semi-major and the semi-minor axis, because in an ellipse, either the width or the height is going to be the biggest, right? That's pretty clear. And these are actually related. So you have not those two. I mean, the period for the planet, and that of course makes sense. So the period of the planet and the semi-major axis. That's what I'm saying. And this period is in years, and the semi-major axis A is in astronomical units. So that's the relation. Yeah. Okay. So we can look at some cases. We already actually tackle it somehow, but we can look at that case anyway. So what happens to velocity when orbital distance increase? I'll just say that it's of course going to decrease, but let's view it. So let's now imagine that we had some, I don't know, planet or comet that had nearly circular orbit, even though that's very rare. That would be very rare, but let's imagine that just to make the calculation easier. Then the velocity is of course just 2 pi, and that semi-major axis, the biggest radius. And then you divide that, of course, by the period, like that. But now we can substitute the period, and instead we could see that v is, of course, because 2 pi doesn't matter, but v is of course dependent on 1 over square root of a, right? So of course the velocity, when you go further, the velocity will of course decrease. That's the idea, right? Okay, pretty good. Okay, the next we are going to do in theory is a two-body problem, which are just two masses and how they orbit in terms of each other, right? That is going to be for another day. I may think it's tomorrow or Sunday, but that's all right. But what we can do are tasks. So let's do some tasks from the last sheet. Okay, not linear algebra, but part A. Here you go. Okay, so let's do. I started on this guy, but we can do that the next time. Okay, we can do this. This is good. Exercise 1A1. Yeah, this is not so important. We will look at some temperature statistics. In order to make it easy, we'll focus on a tropical country where the mean temperature is basically constant all year. The mean temperature, average over day and night in Kuala Lumpur, is about 29 degrees all year. Assume that the fluctuations of the temperature from day to day is Gaussian distributed with a standard deviation of 2. So what we have is that temperature. So we can say that T, the average, is 29 Celsius, and that standard deviation was, what was it, 2 Celsius? Wasn't that correct? Yeah. Okay, so now calculate the probability that the mean temperature in Kuala Lumpur tomorrow is above 30 degrees, which means the probability for that x is, let's see, that small x is bigger or equal to 30. The probability for that is that integral, remember this is a continuous distribution, for that probability function there. So we need that CDF. I could just say CDF, we integrate, and that is of course what is from 30 and to of course infinity. And then what I say, CDF, I could say, that's of course px dx. I think you can write it like that. That should be all right. Okay, where px is that density function. We have to integrate that guy. Okay, and this we do in Python. We already have 29 and 2. So if I go back to Python, I can do this from scratch, but that's boring. It's pretty easy to understand. Okay, so let's go back to the code 1a. So here's the CDF, right? So the mean value is 29. 2 is the standard deviation. And I, of course, just use that normal distribution here. That's the CDF, right? And then we integrate that function and we write just the probability. So you see here, and integrate is just some simple stuff. It's very much like we did that Euler-Kromer there. It's somewhat like, because you see here is the function and just a step, right? Nothing special, just use the properties of vectors here. It's much easier than, it's actually a lot slower if you use that Euler-Kromer instead of doing like this. Okay. All right, so you just do that, nothing special. You can go back. Then calculate the probabilities between 27 and 31. That's of course just one standard deviation on each side. So between one standard deviation, what is that, 67% or 68? I don't remember, that's not important. There's a hint there. Calculate the probability that the mean temperature in Kuala Lumpur is above 30 degrees for the next 7 days. Assume that the temperature one day does not influence the temperature of the following days. Now this means that what we do is above 30 degrees, we take what we got, right, probability, and since they're independent, we of course multiply. So this will just be what we got last time, and then to the power of 7. So you can see that in my code as well. That's this guy. And if you go back here, this one is a little bit more complicated. So here it says, calculate the probability that the temperature is above 30 degrees during 4 of the next 7 days, and below 30 degrees the remaining 3 days. Now this one is more complicated, because what we need is actually, we need that probability that we had, that x is bigger and equal to 30. We need that guy. We need that guy, let's see, and we need that 4 of the next 7 days, right? So 4, so we need that to the power of 4. Then this guy needs to be multiplied by x is less than 30. So of course not equal, so we could just use like this. We already have that, and of course 3. And you can of course write the integral just normal, but just to be a little bit more clear, I can do it like this. Okay, but this isn't entirely correct. And why is that? The reason being is that we have something else. We have also that this is either below 30 or above 30. So this is actually a binomial distribution. So these two are correct, but this is only for one outcome. And we actually have a lot of different outcomes. To understand what I mean, let's say, right, we have above, 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 below, below. That's 7 days, right? But these, they don't need to be ordered, which means that this is also an outcome. A, B, A, B, and then A, and then B, like that. So we need also to take into account how many possible ways we can do this, right? How many possible ways can we shuffle these around, right? And that's of course n choose k. So if you multiply n choose k by these two, you will get the correct answer, which is actually binomial distribution. Because binomial distribution also assume independence. So that will work. And you can see that is how I solve that. So here it is. I have p n choose k. I just made a formula n choose k here. You see just a factorial. And then you could see here is p4, p to the 4th, and then we have p3. Then we have the other side, so minus 1000, stop by 30, and we of course cube that, and then we get that probability. We can run that through. So p1a, 1.p, and then you can see the probability here is 10.49%, which is correct, and so are the others there as well. pretty neat, pretty good, pretty happy. Yeah, okay. Let's see. Now let's move on to linear algebra. What was my linear algebra notes? So when I did last time the chapter 4.2, null spaces, column spaces, row spaces, and linear transformations. It's not a lot of linear transformation, it's just actually null spaces and column spaces. But when I did this chapter, I felt I didn't grasp it really. So I'm going to do it again. I'm well ahead of my of where I should be in the course. So, or I'm very good ahead. So I can do that. So that's very nice. Okay, but let's focus. So let's start. So what is the null space of a matrix and why? Okay, the null space of a matrix. Null space of a matrix is actually the set of vectors that satisfy this equation right here. So what does that mean? We can also write it in a different term. I could also state that it's also that set. I could write that set, let's call this S, and it's equal to X, where A of X is equal to 0. Okay, yeah, that's good, but then you can say it even better. What you can state is that it is the vectors in, this is in R of n, because of course A is m by n, right? It rows. So it is the vectors that are transformed from R of n and then of course into the space. No, that space was bad. Okay, let's do it like this. Yes, perfect. Into the space Rm like that, and they are mapped into the 0 vector. That is what it means. So the 0 vector. So it takes vectors from Rn and they map them to, they transform them into the 0 vector. And that is in Rm. Which means that if they do that, they of course, the x values, they satisfy this equation. So the description here for the null space is implicit. It's like it's a consequence of this guy instead of being something explicit and clear, right? Okay, so that is what it means to be in the null space. Pretty good, pretty nice. Okay. I also said it was the set of vectors, but we say null space. We don't say null set, and the reason being is that this, of course, is a space, right? It just in the beginning we just say the set of vectors, of course, but it is a space. And why is it a space? I did actually the calculations last time. Of course, it's pretty obvious that you can add and subtract vectors. Of course, if I had some vector that went through that transformation, then I of course know that this is 0. And if I do it with another vector that went through the transformation, I of course know that one is as well 0. So if I added those two like that, you could see that of course I have AU plus AV, which of course just 0. So you're still in the same space, and the same with of course multiply. And then actually is the first one is that matters, and there is of course that 0 is there. And 0 is of course there. 0 is in the null space, because if 0 was the vector, of course we're going to get 0. So 0 is of course in the null space, right? Okay, so it's a subspace, and that's why we call it a space. Okay, very nice. We are very happy with that. And of course it's a subspace of Rm, right? It maps the vectors into Rm because Rm is the output, right? But the vectors themselves, what they span is the space in Rn, right? Okay, so they don't have to be 0, of course. Okay. So like I said, this description is implicit. It's not explicit, but we can find the explicit description. And I'm going to do that with an example. So we need to go to linear algebra, right? And here is what I stated. You see null A maps into 0. And here's what I stated, and also this as well. And also this should be pretty clear. But what I want is this guy right here. This is what I want. Okay, perfect. So A is equal to minus 3, 6, minus 1, 1, and minus 7, like that. Then we have 1, minus 2, 2, 3, minus 1. Then I have 2, minus 4, 5, 8, and then minus 4. So now let's find the explicit description. Now I know we need to, of course, satisfy this equation right here, but I'm not going to extend this matrix by adding 0 because I can just write it later. It's just in the way, so it will still be the same thing. Okay, so I'm just going to row reduce like it is, even though, of course, this is what I want, but we don't need that now. Okay, so let's row reduce this guy. 1 is a perf, but I can move that up there. 2, 3, minus 1, like that. Let's see, 2 can that guy. And I also, let's see, if I did 3, then I get that guy. So I also actually want this guy below, because it looks like this guy might die. Minus 7. And then I had minus 3, 6, minus 1, 1, minus 1, 1, and minus 7. And then I had 1, minus 2. No, not 1, you moron. I meant 2, of course. Minus 4, 2. What am I doing? 2 minus 4, 5, 8, and minus 4, like that. Pretty neat. Then we use top 1 to get rid of the bottom one. I always write the top one so I don't lose track. Minus 2, 2, 3, and then minus 1. I multiply u by minus 2, that's 0. I multiply u by minus 2, that's 0. I multiply u by minus 2, that's 1. Minus 2, that's 2. Minus, what did I say? Minus 2. That's of course 2, and that's of course minus 2, like that. We do the same thing, but just multiply by 3, 0, multiply by 3, 0, multiply by 3, that's 6, minus 1, that's 5. Multiply by 3, that's of course 9, then I get 10. Multiply by 3, that's of course just minus 10, like that. Okay, pretty neat. Now what we can do is use the middle one and get rid of that bottom one, right? Shouldn't that be right? And the top one. So the middle one is 0, 0, 1, 2, and then minus 2. Okay, so 0 and 0. Oh, I'm a moron. 1 minus 2. I multiply u by minus 2, that's 0. I multiply u by minus 2, that's minus 4. 3 minus 1. I multiply u by minus 2, that's 4. And then minus 1, that's just 3. Then I do the same thing on the bottom. I multiply u by minus 5, that's 0. I multiply u by minus 5, that's 0. I multiply u by minus 5, that's also 0. And there you go. That should be it, as you can see. And now what I want to do is, of course, what I stated earlier is this, right? This is, and I don't want to do it like that. Yeah. So that's our matrix. So that's just basically a 0, like that. Okay. Pretty good. Now, we want to write this down, actually. So this is, of course, the same as x1 minus 2x2 plus 0 minus x4 plus, of course, 3x5, like that. That's equal to 0. Then we have 0 plus 0 plus, of course, x3. Then we have plus 2x2. Not x2, you moron. x4. Plus 2x4, and then minus 2x5, and that's equal to 0. And the last one is that 0 is equal to 0. Now you can very clearly see that only these two are pivots, and of course the rest here are free variables. But that will be even more clear soon. So we could state that x1, that is explicitly defined, that was our pivot. That's equal to 2 x2 plus x4 minus 3 x5, like that. Okay, then x3 is also explicit. So x3 is equal to minus 2 x4 4, like that, and then plus 2 x5, right? Okay, and now we know that we want x1, x2, x3, x4, x5 to satisfy that equation, which was ax is equal to 0. And that is just x1, x2, x3, x4, and x5. Very good. Then we can, of course, write, do we have an x1? Yes, we have an x1. That's 2x2 plus x4 minus 3x5. Then x2 was a free variable. It doesn't matter. x2, x3 wasn't. That was also defined. So x4 plus 2x5. Then, of course, we have 0, and then we have 0. Okay, pretty neat. We are getting close. But look now. If I now take out the free variables, so let's see. I can describe this the same thing as x2. x2 is just 2, 1, 0, 0, and 0, right? Then I have, of course, plus. And what did I say? Yeah, that's correct. And then, of course, the next one is x4. And if I have x4, I have 1, I have 0, I have minus 2, I have 0 and 0, right? Then I have plus x5. And then, of course, I have minus 3, 0, I have 2, 0, and then 0. And this, of course, describes this guy. You see, here we have it. This is actually the null space, and it's explicitly defined because it's directly defined, right? It's not some consequence of another formula like we had earlier. So now we're actually explicit. And there's a lot of cool things about this solution here. These are free variables, so they doesn't matter, but these guys do. And as you see, a single one of these, of course, can't be mapped into 0. That doesn't make any sense. So these three are independent. And since they're independent, we also know that they form a basis, right? So these three vectors here form a basis. And not only that, these three vectors, by definition then, span the null space. So null A is equal to the span, the set of v1, v2, and v3. So v1, v2, and v3. The set of those three vectors span all the linear combinations of these three vectors here, span the null space for A, the matrix A in this case. So very, very neat. So again, the two properties that this has is that it's linear independent, so we actually have the three bases. And the second one, and all of this is just only applies, of course, if the vectors like these are non-zero. So the first was independence, and the second one that's pretty cool is that you can see that actually the amount of free variables in our matrix, like we had here, the amount of free variables actually corresponds to the amount of vectors that we have for spanning the null space, right? So our basis vectors is actually equal to the amount of free variables, which is pretty cool, right? Okay, and this was also in reduced row echelon form. That's also important, right? But that is how you find the null space. And now we have an explicit definition, right? Okay, pretty cool. Let's see. Okay. Then we have now the next. Of course, after null space, we usually go to column space. So the column space is explicitly defined. We can just state that formula what it is. So the column space, of course, usually with a big C. So the column of A is just, of course, I should have written a little bit better. So we can of course say that A are, of course, these column vectors here. A1, A2, and up to AN, these column vectors here. Then we can explicitly say that the column space, call A, is equal to the span of those vectors there. So now we have an explicit way of saying that. And up to AN, right? That's the column space, right? We can also write it in terms of a set. So call A is also equal to this set right here. We have B, where B is defined as the solution for AX right there. Right, that should be pretty clear, right? Isn't that correct? Yes, column space, A1, AN, etc., right? And why B? Why B like that? Because actually the output B here is of course a part of that space. Remember, the columns here, all of them are going to have m rows, and the linear combination of them also belongs to the span. That's why we use B here in that definition, because that also belongs to the column space, right? Pretty cool. Okay. And now we can do, I wrote to myself, example 4. What was example 4? That's 3. We got that pretty good. What was example 4? Oh, this guy. I've done that before. We don't need to do that. That's all right. Okay, the last thing I stated in my notes was the column space of an m by n matrix A is all of, yeah. So of course, if in the column space, if we have a solution for each B in R of M, right? So B, B1, B2, right, is the dimension, oh, not, you can say it like that. If we have a solution for all the B's in R of M, then of course we should span R of M. And that of course means that the column space will span R of M. That is what it means, right? So for example, I think if I had a single solution maybe, yeah, this is a detail that's not that important. I know what it means in the feel of it, maybe. How can I say that? Yeah. This definition is a little bit weird. I know what it kind of means. Okay, let's try again. The column space of an n by n matrix A is all of Rm if and only if the equation Ax equal to B has solution for each B in Rm. Yeah, so for each B. Oh yeah, of course it should be. Of course it spans. If it has a solution for every B, right, okay. If I have a solution for every B, let's say B is in 2 dimensions, and I have for every single one of B, of course I have to span the whole of 2 dimensions, right? If B was in 3 dimensions, and I want for every single B, it's not just the components, it means every single B. That's what I mean, that's where my confusion was. If it means if we have a solution for every single vector in 3-dimensional space, of course, we are covering the 3-dimensional space. That makes sense, yeah. So that's it. Okay, pretty good. Now let's do some tasks. So I did some tasks from the last chapter. So let's see that. We can just do 2 of them. The others were pretty simple. What did I do? What was the actually? I need to know. Let's see. I need math here and notes from the lecture. No, weekly 2, 5, 12, and 15. 12 was the one I hadn't do, and 44. So let's do 12 and 44, right? Okay, 12. Let V be the set of all vectors of the form. Show that, no, not V, show that W is a subspace of R4. Use the method of exercise 11, right? Okay. So V, I can just write that set. I'm gonna change back, but I can write that as a set. So that is S plus 3t, S minus t. And then we have 2S minus t and 4t, right? That's the vector. And we of course have S and t as real values, like that. Perfect. Now we have to show that W is a subspace of R4, right? If it is a subspace, like we have done earlier, if it spans R4, it's of course not the whole, but if the vectors are in R4 and we can create a span of them, they're of course a subspace of R4. That's one of the theorems we have. Okay, so let's see if we can do that. So if we can write this, let's see if we can write this as a span. So we need two vectors that span, of course. Okay, did I want that as a matrix? Yeah, subspace, that's on it. Okay. So what we can do is that we can state that vector u is equal to, of course, s. Then s is just 1, 1, 2, and 0. And then v is, of course, equal to 3, minus 1, minus 1, and 4. And now you can see pretty clearly that u and v, now we have taken out, oh, I mean t there. Now we can see pretty clearly that u and v, of course, the span of u and v, so let's say S is equal to the span of u and v. The span of u and v is, of course, the same. The set is the same as W. And we know that the span of u and v, since they are in 4 dimensions, they are a subspace of 4 dimensions. Which means that W is, of course, also a subspace of 4 dimensions, like that. Pretty good. And the last task, I'm just going to explain that because it's so painful to do. Is this 44? But it gets really ugly. It's pretty easy, actually, in terms of just logic. So determine if Y is the subspace of R4 spanned by the columns. Then, of course, you can extend this guy by this guy. Of course, if you get a solution, then of course it's a subspace. That's it. It's nothing more than that. No, of course it's in the subspace. If Y is a solution and you put it in this matrix, of course it's in the subspace. But when you put it in, it's pretty painful. These are not nice values at all to work with. But that's the approach, and then you solve it. Okay, so that's it for today, and I'll see you tomorrow.